Good evening, everyone. Welcome to Unit 3, Work, Energy, and Power. Hope everyone's having a wonderful Thursday. Let's dive in. All right, so what is work? Work is a push or a pull, and we did this last week, right, with Newton's laws. But now we're interested in finding work over a certain distance. Like if you push a car up a road, you'll be applying a force onto the car, but you'll also be traveling a certain distance. You'll be applying the force over a certain distance. Same thing, dragging a bag across the floor. Like you care about how far you go, because there's two aspects to it. There's the amount of force that you exert, and there's also how much your distance or displacement is going to be. So work is this measure of how we basically how we measure force being applied over a certain distance. And specifically, work is the product of the force being applied to an object and the displacement of the point of application of the force and the cosine of the angle between the force and the displacement vectors. So in short, W is F, which is our force vector, delta R, which is a vector or displacement vector, and here we're actually taking the magnitudes of the vector and we multiply it by the cosine of the angle in between. So, as a quick example, if you have a box, right, and you are, say you're a person over here, and you are, moving the box, a very big box, from point A to point B. Okay, now this is your displacement vector R, and you're going to be, let's say there's a rope over here, and you're going to be, applying a force this way. Well, the work that's done is essentially this vector times this vector, magnitudes, times the cosine of the angle in between. And what this lets us do is, by taking the cosine, we get the component of the force along the displacement vector. So, if your vector that you're pulling is vertical, the work's going to be 0 because you're not even, your cosine of 90 is 0, and also you're not going to be pulling the box anywhere because you're just pulling it up vertically. And yeah, so, and if it's perfectly in line, then you have, full efficiency basically, because you're pulling directly into the displacement vector. And work is measured in joules, which is Newton times meter. Makes sense because Newton is from force, meter is from R, cosine is unitless. And yeah, it gets its own unit, the joule. A little bit more about work. So we want to think of work now as energy transfer. And we've done this in Physics 1, but on the AP test for Physics C, the problems are going to be harder, and it's really your intuition that's going to get you through the free response questions. So we want to think of work as energy transfer. So pushing and pulling a box on the floor over a distance requires energy, right? Like if you were to, lug a box all the way across the floor, is going to require more energy than if you were to just lug it a few inches. Another example, a spring deposits energy into a system when it launches it over a distance. Slowing a ball rolling down a hill requires energy, right? You have to kind of push the ball in the opposite direction of the motion. So in general, there's two entities. There's the agent and the system. And you can think of like James Bond as being the agent, and the system is, some observable scenario, classic physics problem, and the agent is now going to be doing some kind of work onto the system, is going to be helping out the system in some way. And this is a convention, so if work is positive, energy is being transferred into the system. And you would hope so, right? Like if I say that I did 10 joules of work, right? Positive 10 joules of work, well, I would hope that I'm, providing more, I would be transferring energy into the system, versus negative 10 is like I've kind of taken out from the system. So yeah, think of yourself as an agent pushing a car so it speeds up. So does this require Is this positive work or is this negative work? Well, you're increasing the car's kinetic energy. We can assume, let's just assume potential energy is the same. It's a flat road. So your work is going to be positive. Your car is going to start with small kinetic energy and it'll become big kinetic energy. You're adding energy into the system. So, I misspoke. We're actually slowing down the ball. We're slowing down the car. So we start off with, my mistake. We start off with the car going really fast. So there's high kinetic energy. And then we push the car so it slows down and it becomes less kinetic energy. So we're removing energy. So the work is negative. In the situation I just described, my slip up, if the car is going from slow to fast, right, then we're delivering energy. If it's going from fast to slow, we're removing energy. And the mnemonic is that positive work, it's harder to do physically. Like you have to speed up a car versus slowing down a car. You can think of which one's easier to do. And positive work is going with the direction of the motion. And negative work is opposing the direction of motion. And this completely comes from F times R times cosine theta. So the question is like, these two are positive, right, quantities because they're magnitudes, and cosine of theta is negative, right, if we're going opposite direction of motion, right? You can think of, where cosine is going to be positive here and negative here. Awesome. Now, in the special case, work with constant force, that's this relationship here, right? This is the dot product. So this is the formula for work done by a constant force. This is not always the case. Sometimes we have work with varying force. So instead of pushing up a car now with pushing a car with constant force, suppose you increase your force after each meter, or suppose the force that you pull changes. Maybe you start off slow, you start off like pulling gently, and you go harder. It can change. And the way that we think about this is we're basically going to integrate we're going to add up a bunch of small segments. So this is a general formula. Like we're going to assume that the applied force is a function of position. So this function here, F is, F is a force. It's a function of position, meaning that at every specific point on the x-axis, let's say, I can give you a value as to what the force is at that specific point. And then we integrate with respect to position. Same thing using vectors. And the way to think about this, of course, is, if this is your path, if this is your like delta R vector, you start here and you end here. We're just going to divide up, your path into a bunch of small segments here. The width of the segment, or the length of the segment, is dx. Each one is going to be dx. And we're going to say, oh, what is the force along just this small portion of the segment? Well, it's going to be F evaluated at that point. So it'll be F times dx. And here we're just going to assume, cosine will drop out that term. If you can always replace the force with the component that's projected onto the axis of displacement. So we're just going to say, this is the work done on the small segment, and we're going to integrate, which means that we're going to sum up all these small segments to get the total amount of work. Okay, let's look at an example. So the work done by a spring. Okay, so recall that a spring applies a force F equals minus kx. We looked at this formula before. This is just from other things, other units. Remember, for a spring, the force, it's a vector, has a constant proportionality times x, and it's negative, meaning that if your x, if you're displacing it a certain way, the force is going to be going the opposite direction. Does that make sense? If we pull a spring, right, it's gonna try to go back to equilibrium, so the restoring force is gonna be opposite the direction of displacement. And we're going to consider these regions. So over here we have equilibrium, here we have x equals minus x max, and here is x equals x max. So this distance here is the same thing as this distance here. And imagine this spring is moving, and we're going to say, what is the work done by the spring on the box from x equals minus x max to x equal to 0? So what is the work done by the spring on the box? So what is the agent here? It's going to be the spring. So the spring is kind of like this external thing, and on the box is like the system. And what we're wondering is this spring adding energy to the box, or is it taking away energy from the box? That's kind of how we're going to think about it. So spring force is a restoring force, right? It goes, so the direction of the force is the opposite. Oh, that's very wrong. Is the opposite of the direction of the motion. So you displace it, and the restoring force will cause it to go the other way. This is very wrong here. Wait, what is restoring force, right? The spring wants to remain uncompressed, so it will restore itself to its original shape. So F equals minus kx. So what is the work done by the spring on the box from here to here? Well, what we can do is we can just integrate, right? Because we have force as a function of position, right? So we can use our formula from earlier. Work is equal to F dx, right? And we get what? We're integrating from minus x max to 0, right? So this is kind of like what I was saying earlier. You have you have your distance traveled, and we're going to be adding up a bunch of these small, the work done over here plus the work done over here. We do that by an integral, and it's just substituting this in. Our lower bound is minus x max, our upper bound is 0, and this is our force. This is dx. When we integrate, we get this over here. And here I just copied, just from the earlier slide. If we now evaluate our upper and lower bounds, right, we get this minus this is equal to this here. So our work is 1/2 k times x max squared. So the work done from here to here is positive. Does this make sense? Let's think about it. So what is the direction of motion of the box? Well, when it's over here, you can imagine the spring is very compressed, and then when it goes, when the box is going to be traveling this way, right? So this is R, of course. Now, just imagine the spring is compressed, and we go here, it slowly uncompresses. It probably quickly uncompresses and goes back to equilibrium. Now, what is the direction of the force then of the spring? Well, this force is also going to be in the same direction. Does that make sense? Okay. Now, let's think about the next portion. So let's say now, suppose we're considering from x equal to 0 up to x equal to x max. Well, now the direction is still the same. It's delta. It's we can call this in the positive x direction over here, x positive, and our force now is going to be where? Well, remember, springs want to go back to equilibrium. So if you ever are wondering, where is the force? Think about the spring wants to go back to equilibrium. So when the box is over here, the spring wants to go back to equilibrium. So where will the force go? Well, it'll go this way over here, F. Let me write that a little bigger, F. So in this configuration, R is going this way, and F is going this way. So opposites. So that means that the work done is negative. Okay. Now, suppose that the spring is a nonlinear spring. So sometimes you might have a spring that has a different characteristic, and in that situation, we won't do the problem, but all you would have to do is, instead of, when you do work equals the integral of f dx, instead of substituting f equal to minus kx, we would just substitute in whatever function. So it would be here minus this quadratic, and we would just do the same analysis. Okay, now let's look at the work kinetic energy theorem. So, kinetic energy is a type of energy, right? And the work kinetic energy theorem and all these conditions must hold. So, work done on the system, kinetic energy is, just a reminder, is 1/2 mv squared. The only change must be speed, and the net work done on the system, and this is the key thing, equals the change in kinetic energy of the system. So just to reiterate, the work kinetic energy theorem, there is only kinetic energy and there's work. So we're not considering potential energy at the moment. And you can, the best example is, if you think of a ball moving and you apply a force to slow down the ball. So the kinetic energy of the ball, right, is what? It's 1/2 mv squared. 1/2 mv squared, and initially the ball is moving really fast, right? And the kinetic energy is really high, and the ball slows down. Kinetic energy is very low, and you applied a force to cause this change in kinetic energy. And that's what this work kinetic energy, wow, I can't say that, theorem is. So your work applying the force has caused the energy of the system to decrease. And now we have to think, okay, so is it positive or negative? Well, there's two interpretations. So one is the applied force will be opposite to the direction of the motion. So, if the ball is going this way here, or as a displacement vector, how do we slow it down? Well, you want to push, opposite. You want to push opposite this direction, right? So your force is going to be that way. If you push in the same direction, you're just going to speed up the ball. So because they're opposite, the cosine is going to be negative, so we have negative work. Alternatively, we removed energy from the system. This is a better way to think about it. We started off with high energy, now we have low energy. We've removed energy from the system, so our work that we've performed is negative. We haven't helped the system. In fact, we've done the opposite. We've taken away energy from the system. Okay, so how do we solve these type of questions? Well, we're going to primarily look for context clues about energy. So, there's potential energy, which is moving up a ramp. There's kinetic energy, car increasing its speed. Elastic potential energy, which is a wound spring. And, you can remember the energy checklist from the last unit, and you can kind of use that when you construct free body diagrams. And based off of that, look for springs, right? Because springs is a force, has a force, but also has an associated elastic potential energy. You can look for your gravitational vectors, right? And that'll help you find out where there's potential energy. And if there's an applied force, that'll help you determine, like the work, like the force associated with the work. Kinetic energy, you kind of have to eyeball it. And a few things to consider: is the potential energy the same at the start and the end of the path, right? Because potential energy, we just care about the difference in the altitude. Has kinetic energy changed? Situations involving force across a distance, like if you read a problem and it says, a 5 Newton force is being applied over a distance of 5 meters. Or if there's something that's changing speed, another indication. So just to review, potential energy, gravitational potential energy specifically, it kind of deals with the configuration of the system. So, we care about the, basically we care about the vertical height from the core of the Earth. And we have a unit dedicated to this, but, this is all what we need to know right now. We care about like the start position and the final position. So what this part here is saying is basically we don't care about the actual potential energy and like in numbers. Like we can't even determine that really, but we care about the difference. We care about like from here to here, how much has it changed? We don't care if this is 100 and this is 105, or actually if this is 100 and this is 105 versus this being 200, this being 205. We just care that this is a difference of 5. We don't care about the actual numbers. And the way we do this is we pick our reference point. We say that the absolute gravitational potential energy here is 0, and then everything else is calculated with respect to it. So let's say like we have here point A and point B here, and let's say that our reference point is like over here. Then you know, our change in potential energy from A to B is going to equal what? Well, it'll just be this change here. So change from B to ref minus change from A to ref, right? So here to here minus here to here. And that's basically the change from, this would be B to A then, B to A. So here to here, it's just this difference minus this difference. So you can see like, you know, we can arbitrarily, we can assign this reference point wherever we want and won't change our answer. So generally we choose our reference point to be one of our either starting or final positions. And just to remember, gravitational potential, like if we have a system containing a large mass in the Earth, like you'll see a question of maybe like a satellite is orbiting the Earth, or like the moon and the Earth. These are like very big objects. Then the gravitational potential is given by this. So we can't really use our approximation. Like we can't really use this approximation anymore because now we have like celestial bodies that are a lot bigger. And the 0 or reference potential energy is at an infinite distance from the Earth. All right, so some vocabulary real quick. Potential energy refers to gravitational potential energy. It also refers to the elastic potential energy of a spring. And the mechanical energy of a system is, you know, this exact same potential energy plus kinetic energy. Now, that's it on energy for now. Let's just switch gears for a tiny bit back to forces now. And there's going to be a relationship that will determine very soon between forces and energy, but we need to go back to forces for a second before we can build that difference. So there's two types of forces. There's conservative and there's non-conservative or dissipative forces. So non-conservative, dissipative, they mean the same thing. Just depends what textbook you're reading. Now, conservative force is a cool one. So if the work done on an object only depends on the initial and final position of the object, then we say it's a conservative force. So gravity, for example, is the best example. We just care about the start and the end position. Now, what about a human pushing on a box? Now, do you think that if you were to push a box, 1 foot to the right versus pushing a box an entire mile, do you think that the work that you performed is the exact same? This is meaning like you're pushing a box from point A to point B, either this way, or if you travel, a mile and, do the same start and end point, but you travel a different path. Do you think you performed more work? Yeah, you probably did, right? It took a lot of effort to push the box, a lot of friction involved. In fact, friction is the first example of a non-conservative force. So friction, resistive forces, usually gravity is the main conservative, and usually everything else tends to be non-conservative. Gravity just for now. Okay, so conservative forces are special because the amount of work only depends on the initial and final position. So in other words, the amount of work is independent of the path. However you go from A to B, it doesn't matter. You're still going to do the same amount of work. And there exists a relationship between the said force and the change in potential energy function of the system. So this is a mouthful. So delta U, what is that? That's our change in potential energy. So that's like how much, that's your MGH, your change in potential energy. And we're saying that this equals negative this integral here. Now this integral is made up of two parts. Made up of your force times your, oh wait, that's work. So your change in potential energy is equal to work, and the work is specifically the work done by the non-conservative, by the conservative force. So F here refers to the conservative force, and what we're essentially doing is we're integrating over the path that the object takes from point A to point B. And like we said earlier, adding up these small things, and this is your work, and it's a change in the potential energy of the system. So this is from the previous slide, and if you differentiate both sides of the equation, well, if you differentiate this here, you get this, and if you differentiate over here, you get F, and we put the minus sign on the other side. So these two formulas, of course, are equivalent, and we should know these formulas. They'll come up definitely in a multiple choice question. So conservative force is tied to a potential. They come in pairs. So for example, gravity is a force with a gravitational potential. Gravity, mg, has a gravitational potential, mgh. A spring has a restoring force, minus kx, with an elastic potential, minus 1/2 kx, or 1/2 kx squared. Okay, so let's just go to the example real quick of a spring. And this is the same formula from the previous slide, and all we're going to do is we're going to look at a spring, and we're going to check if our formulas make sense. Like we know there's a kx minus kx for force, and we know there's a 1/2 kx squared for potential. And what we're going to do is we're going to just see if it holds. So delta U, change in our potential energy, is minus the integral of kx, which is our force. And if you do this integral, you can you take the minus k out of the integral because it's a constant. You integrate just x, becomes x squared over 2, evaluated from A to B, and substitute it in, and you get this here. And this does the same thing as 1/2 k times b squared minus a squared. And our delta x over here, our force here, is equal to minus the derivative of the potential, which is just minus 1/2 kx squared. And oftentimes, like, we'll just set we'll just set like a here, we'll set it equal to 0, meaning like it's at equilibrium. That's where we get the 1/2 kx squared. If it's not at equilibrium, you would have like 1/2 k x1 squared minus 1/2 k x2 squared. And we take the derivative, and the derivative will power rule, so 2 times 1/2 just becomes kx, and the minus sign stays there, so you get minus kx. And yeah, this looks good to me. Like, force is minus kx, which we derived from the potential, and our potential is 1/2 kx squared, which we derived basically from the force. So this holds. Okay, now one more thing. This always comes up as a multiple choice question all the time. You'll get a graph of U, or you'll get a graph of F, and you're going to be told to sketch the other one. So if I give you U over here and I ask you what is F, don't look over here for a second. How would you do it? Well, at first you would be like, oh shoot, how do I do this? Because I don't have a function. But then you realize, oh well, F is what? F is minus the derivative, right? And if this is a quadratic, suppose it's like y is equal to like 2x squared, right? We know it's going to be somehow an upward opening quadratic, and you know, it'll be shifted over here, but it's fine for now. And if we take the derivative of this, so remember, like, you know, our y here is technically u of x equals 2x squared. And if we take the derivative, so du of x dx, we just get 4x. And we know that f is equal to minus that, so we get f is equal to minus 4x. So we know it's going to be some, you know, downward sloping line, linear. So we will get something like this over here. And to go the other way around, all you have to realize is that, you know, this plot, if we're just given our f, our force, we know that this would be like some form of, you know, f of x is equal to minus, I'll use a different number, let's say like minus 10x, because we know it's like some downward sloping thing. You know, if we were to integrate this, what would we get? So we get minus the integral, and this is u, will be minus the integral of minus 10x dx. So we would end up getting minus, minuses would cancel out, so we get a plus. Then the 10 we can pull out times the integral of dx. So we get 10x squared over 2 plus some constant, which is 5x squared plus a constant. So we would know that it's some kind of parabola sloping upward. And we get a graph over here like that. And the one thing just to double check always is, you know, you can get the shape right, but we want to make sure that it's like the location is right too. And to do that, the trick is that where this is 0, where the, you know, force is 0, and remember, this plot here is the derivative of the plot on the left. Well, where is the where the derivative of 0 corresponds to the vertex. So you just have to make sure, like, if this is at x equal to a, that this over here is also at x equal to a. You just want to make sure of that. Yeah, so that's one free multiple choice question, because it's definitely going to come up. Comment down below. I'm very curious if it still comes up. Now, one more thing. So, say we're given two potentials, mu1 or u1 and u2, and we're wondering like the stability of this. So what this means is like you have this like kind of potential across the x-axis. So you can imagine putting a ball at the origin, and we want to wonder, like, if we move the ball a little bit to the right, is it gonna, you know, fall off? Is it gonna keep going in that direction, or will it come back to our original? We'll come back to our original point. So think about it for a second, and then we'll go through it together. All right, let's look at it together now. So imagine putting a ball at the origin here, and if we move the ball slightly to the right, what's going to happen? Well, what we're interested in is what is the force being applied to the ball. And what I remember is that we're given potential, which is u, and we can get force from minus the derivative, right? And, you know, what is like at this point over here, like if we zoom in over here and we say, like, what is the derivative at this point over here? The slope of the line is positive. So that means the force is negative because we have minus the derivative. If the force is negative, that means that we're moving the ball in this direction here. So what is this saying? This is saying that if we move the ball slightly to the right, the force, restoring force, due to this potential is going to push it back to where it started. So we have stability on that side. And you can do the same thing. On the other side, if we move the ball a little bit to the left here now, what is the restoring force? Well, the slope is negative, so F is positive, which means that F is going to go this way in that region. So either way, you move the ball left or to the right, it's going to go back to the center. And in this U2 here, the complete opposite happens. So if the ball is over here now, and we move the ball slightly to the right, then the slope is going to be negative, so the force is positive. And similarly over here, the force is negative. And what this means is that if you move it to the right a little bit, it's going to keep going and going and going because there's going to be applied force moving it continuously moving it in that direction. So the ball kind of just escapes that point. And yeah, remember these are graphs. Like, don't think of it as gravity. It's like very tempting to think that, oh, it's going to fall off the hill, but don't think about that because it's a graph. It's not like the physical thing. But you know, by all means, it is a helpful mnemonic to think about. And the one cool thing that you might notice is that we chose these graphs for a specific reason. So this u is kind of the form of u is about 1/2 times some constant times x squared. And the corresponding force from the previous slide is something of the form of F is equal to minus kx. So these are actually the graphs of a spring. And if you think about it, this point here corresponds to the equilibrium position. And the stability is saying that if you pull the spring a little bit, there's going to be a restoring force going back to equilibrium. So if you have a ball that's attached to the spring and you move the ball slightly to the right, the restoring force is going to push it back to equilibrium. So that kind of shows how springs are stable. All right, so now we know we've just explored this relationship between conservative forces and potential energy. Let's go back to energy now. End of our detour. So conservation of energy. So if forces internal to a system are acting on an object in a system, the total change in mechanical energy is 0. Remember, total mechanical energy is kinetic plus all of our different potential energies. And the work done by a non-conservative force is going to be the change in the energy. So all this is saying is that you look at your system in the start and the end state. We're just looking at the mechanical energy of the system. And what we're saying is that if there is an external force, a non-conservative force, then we're going to be modifying the change in energy. So, you know, we have a start energy, we have an end energy, and the difference is due to this non-conservative force. Does that make sense? And of course, you know, if the start and the end force are the start energy and the end energy are exactly the same, then there's no agent delivering or removing energy from the system. And you might be thinking like, oh, well, okay, this is non-conservative force. What about the conservative forces? Well, think about like, you know, gravity is a conservative force. And we kind of embed this into gravitational potential energy. Okay, so just you know, we've kind of like you know, dropping a ball, right? You know, you have at the very top, or potential energy is very high, kinetic energy is very low. In the middle of the fall, you know, it's kind of like being shared between the two. And then at the bottom, when it hits the bottom here, there's 0 gravitational energy. And, you know, this is our reference point here. And, you know, there is going to be a speed associated with the ball. There will be a velocity associated when it hits the ground. So the velocity, like the kinetic energy, is not going to be 0. We just don't have an expression for it right away. Now, applying the conservation of energy, well, best example is Atwood machine, which we'll look at in a few minutes. The speed of an object under the influence of a spring, the speed or positions of objects moving under the influence of a non-constant, one-dimensional force. So what this is saying is that you have a ball that's moving, you know, speeding up or slowing down from point A to point B, and there's being a force applied, and the force is a function. It's non-constant. That's where we would use your conservation of energy. Also, you know, these celestial kind of problems, astronomy problems, which we have a unit on that. So here's a cool example. All right. We have a mass over here, and I'll just summarize it real quick. So you have a mass over here, The mass over here, we have a spring, right? And we have a frictionless pulley. Okay, maybe I should just read it. So we have a mass over here. It's held in position on a 40-degree incline, so we know this angle, with a coefficient of friction. Okay, there's friction involved. Is friction conservative or is it non-conservative? It's non-conservative, right? Because we're gonna need that because in our conservation of energy we have a work non-conservative term. So now I'm thinking friction might be that term. A string runs parallel from its top surface over a frictionless pulley. Okay, there's no friction, internal friction here. It's a light spring, we can assume. And we have another mass here, 30 kilograms, that's attached to a spring. It's attached to the ground. Okay. Now we're gonna pull this mass here 20 centimeters down from the incline, and then we're gonna release it. Okay, so I pull it, release it, and we want the speed of this mass over here as it passes through the equilibrium position of the spring. Okay, so basically pulling the bottom box, and we want the speed of the other box when it's at a certain point, and that certain point is the equilibrium position. A lot of things at play here. Let's take a look at what we can do. Yeah, so there is a non-conservative frictional force. And just to summarize, there's two timestamps. So the first timestamp is the moment the mass is pulled down the 20 centimeters. So we pull it down over here. That's our first snapshot that we can take. The second one is the moment when the other mass passes this equilibrium position. Then we can take our next snapshot. So we have point A, we have point B. Now I'm thinking that we have 2 points. We probably have energies associated with both points, and maybe we can apply the conservation of energy to figure out, because speed, velocity, that's a term in the kinetic energy formula. Kinetic energy is 1/2 mv squared. We know m, we want to find v. Probably we can dig it out from that. Yeah, so part of the energy, okay, so this is kind of a great way to think about it. So part of the energy is dissipated due to frictional force. And to think about this is initially the energy is great. It's really big. Think of the energy, having energy before, and then adding work due to friction and ending up with less energy. And this is because friction, the work done by friction is negative, right? Because the force goes opposite direction of your motion. So just remember, like F equals, your force is equal to your work is equal to your force times your delta r, which is your displacement vector, times the cosine of the angle between them, right? And for the specific case of friction, and this is the same thing as the dot product of the two, your dot product is going to be negative because your force is going one way and your motion is the other way. So this is a negative term. So this ends up saying that if this is negative, that means that your before energy is bigger than your after energy. Okay, so let's look at the first snapshot. Okay, so this is when we've moved the first box, the shaded box, down 20 centimeters. So what is the non-conservative forces? Well, friction. Remember, this is like the left-hand side of the equation over here. So this is what we're looking at right now, basically. The first snapshot, energy before. Also, we want to look at the work that's non-conservative. So the non-conservative force is friction. We'll have to determine what the work is. The kinetic energy, is there kinetic energy? Not really, because we pull it down and we kind of release it, right? So when we pull it down, there's no kinetic energy. When we release it, it goes to the next position, then we have kinetic energy. We have things that are moving. Potential energy, yes, there's two types. So we have gravity and we have our spring providing our elastic potential. So what is our elastic potential? Well, the spring is elongated when we move the block 20 meters or 20 centimeters. Okay, so how much does the spring elongate? 20 centimeters also, right? If we move this down 20 centimeters, the spring is also going to move 20 centimeters. So elastic potential, which is 1/2 kx squared, we're given k, we're given x, as as 0.2 meters or 20 centimeters, and yeah, we would know what this term is. So far it seems like good shape. Gravitational is usually easy to figure out. We know our current point, we know our final point is going to be somewhere 20 meters in this direction. And similarly here, this one's actually easier because only vertical. We would know our gravitational potential at our start. And remember what I said, we don't care about the start and the finish values, we care about the difference between the two. So we might do something where we set the reference to be probably the starting point or maybe the ending point. But we'll look at that in a second. But the main idea here is that in this first stage, we know our friction is our non-conservative force that'll give us our non-conservative work, and we know our total energy is going to be due to only our elastic potential and gravitational potential. And let's just write it out. So UG1, gravitational potential for this, UG2, USP due to the spring, and plus our work, non-conservative. So actually, technically this here is our energy due to mechanical energy, and this here is our non-conservative work. And remember, mechanical energy is potential and kinetic, but we don't have any kinetic, so it's just potential. Okay, now let's look at the second point. Now our work is friction, right? But it's only on the left hand side of the equation, so we're not going to really include it on the right hand side, but it's good to think about. Do we have kinetic energy? Yes, this time we do. We're being asked to find the speed of this object. What would the speed of this object be? If our final answer is our speed is 10 meters per second, let's just say, what would be our speed of the first object? It would also be 10 meters per second. It'll be the same thing because they're both moving together. If they're moving at different things, this string here would be different. It would either stretch out too much or it would shrink, and that's not possible. So just to remember. Do we have any elastic potential this time? We actually don't, because we're being asked as it passes through the equilibrium position. So our 1/2 kx squared would be 0 because our x is 0. We don't have any displacement from equilibrium. Gravity, we always have gravity. Okay, so our energy afterwards, remember, we don't include our W and C. We don't include that in this side of the equation. It's just kinetic energy 1, kinetic energy 2, plus gravity 1, plus gravity 2. And now we're ready to equate the two. So we can say that this here is our energy, this is our work, non-conservative, and this is our energy after, before. Ooh, my handwriting will get better, I think. It's a little hard to write on. Okay. So far, so good. Okay, now let's just substitute it in. So you might have done this problem a little slower, but the approach is what matters the most. We looked at 2 points in time. We wrote it out in variables. Now let's simplify it a little bit more in terms of variables. Let's expand upon all these quantities. So we're going to set the initial, we're going to set our initial, we're going to set our initial box here, position 1, you could say, start position, to be our gravitational reference point. And our final one is going to be our whatever it's going to be. So let's just say gravity here 0, 0, And our spring is going to be something like this here, where this is our kind of displacement from equilibrium position of the spring. And what is that, by the way? Oh yeah, it's 20 centimeters, right? That's how much we're pulling this box. So it's the same thing as how much we're pulling this spring. And work non-conservative, this is going to be, something of this here. We'll get into this on the next slide, I believe. It's just our friction force, which is mu k times the normal force times the cosine of the angle between, because W is force times displacement times the cosine of the angle between. This is our force, this is our displacement, that's the cosine. Kinetic energy, 1/2 mv squared, 1/2 mv squared, and then mgh is 2 of them for both of our gravitational potentials. Let's look at this even more now. Okay, I tried color coding this to make it easier to follow. Do let me know if this is like easier or if it just makes it cluttery. Yeah, so in the problem we're given these. We're given K, our spring constant. We're given 200 newtons per meter. We're given M1, we're given M2, and we're given the frictional force, or our coefficient of friction, which is 0.15. And do remember, like, if they don't specify static or kinetic and it's just one, you can assume that's one you're going to work with. So frictional force, this is our green term over here. Well, mu k we know that. What is Fn? Fn is our normal force. Normal force is the force exerted by this thing over here pushing up against the box, perpendicular, of course. It's the same thing as that component of gravity, right? Like in that direction, in this kind of perpendicular direction of the ramp, there's no motion, right? So our normal force, which is pointing upwards, has to balance out the gravity that's pointing the opposite way. So if this is our gravitational vector here, then our this green component, I colored it black now, but that component over there is going to be what? Well, it's just going to be gravity, which is mg, times the cosine of this tiny angle here. And the reason why is because, this angle here and this angle here are the same. Why? Because of geometry. Like this guy here, if you extend this out, is complementary, or with this one over here, and then these two are both, let me clean it up a little bit. You could think of like this angle over here, which is 40 degrees. This here is also 40 degrees because these two are parallel lines, and this here are complementary, and then this is perpendicular, so that means that these two must be equal because these two are complementary and these two are complementary. Just in case we forget. So this green thing here is just going to be the cosine, so we get this as our final portion of gravity that's perpendicular, which is the exact same as the magnitude of the normal force. So the normal force is also going to be perpendicular. The green arrow doesn't really look perpendicular, to be honest, but now that I look at it, but it is supposed to be perpendicular. So that's our normal force. And the distance, so we know mu k, we know Fn now. Now I just need to know these two terms. The distance is going to be 20 centimeters. And the force of friction, we know that force always goes opposite the direction of motion. So our phi cosine of the angle is going to be cosine of 180, which is -1. So that's this term. So we know all this green term. Let's look at this purple or pink, purple, fuchsia colored term over here. Well, the spring is going to be what? Well, 1/2 k, we know what k is. x0 and versus x, this is just going to be our displacement from equilibrium. So one of them is 0, the other one is going to be 0.2. We moved at 0.2. Okay, now what about the right-hand side? So we kind of solved this left-hand side. Now over here, we know what M1 is. Oops. We know what M1 is, and we know what M2 is. Half, of course, we know. We're solving for V, so we can't really do much with those two terms. But it is good to know that we have one unknown so far that we're solving for, right? It's not like we have two unknowns. That would be terrible. We have one unknown so far. And let's look at this term here. We know what M1 is. We know what M2 is. We know what G is. H1 and H2 are the only terms that are missing. Now, what is H1? Well, H1 is the hard one. And the reason why is because, you know, it's like at an incline here. And I'll just quickly like zoom in onto the first box. This is box 1 here. So if we start here, and if we end over here, right, and over here, then we're wondering what is our change in our gravitational potential. Well, you can think about it just like, you know, as a kind of like a triangle over here. So this is our change in H, and that's basically the H1 that we're trying to solve for. And how do we do that? Well, we know the hypotenuse is 0.2, because that's how many meters that we've pulled the box. What we're wondering is, what is this change in height? Well, it's just going to be 0.2 times the sine of 40 degrees. So the sine will give us this vertical component here. And H2, of course, is going to be, this one's easy, right? Because the only displacement is in the vertical position. So it's just going to be 0.2. Quick recap here. I think we've solved everything on the right-hand side except for V. We know everything on the left-hand side. So it looks like we're good now. Okay, let's plug it in. So 1/2, good. K is 200. X0 is 0.2. You can take my word for it that, you know, this term here is 0. This is our, you know, it's minus, right? Because the cosine of phi, we said phi is 180, so we get a -1. So minus mu k f, mu k fn, which is m times g, and times the cosine of 40 degrees, which gives us the, you know, which gave us like the specific component of gravity that balances out the normal force, times r, which is 0.2. And then the right hand side is 1/2 v1, which is the same thing as v2, right? Because they both travel at the same speed, times m1 plus m2 and mgh1, mgh2. We know what h1 and h2 are, and using help from h1 and h2 are, you know, these two values here. And, you know, if you solve this here, you can take my word for it, you get this as the final answer. So a little under 1 meter per second is the speed of this mass as it goes through the equilibrium position. So at a very, very high level again, we started off by using this equation here. And we said that we know what our potential energies are, we know what our kinetic energies are before, we know what they are afterwards, and we know that the non-conservative work, which is due to a non-conservative force, is going to be the friction force. And using that, and using, you know, these small things like, if, you know, if a system is moving and we're at the speed of one thing in the system, the other thing is going to be moving at the same speed. You know, if we move the system 0.2, everything's going to move 0.2, not just that one thing. Just using these small, like, simplification, like these small things, we were able to come up with the answer just by using this conservation of energy. Awesome. Now, there's one small last topic, which is power, and that's actually it for this unit. So power is, you know, it's not a super big topic on the AP exam. You might have to take a derivative, but it's worth mentioning. So, you know, force is a push or a pull, right? Energy, work is force over a distance. Power is like the rate at which the force, or energy actually, does work on an object. So it's kind of like saying that it's a change in energy per second. It's like dE dt, change in energy with respect to time. So what this is saying is, like, if we're looking at work, for example, energy is what? Energy is the same thing as work. Work is F times R. So I'll just write that down. Like, energy and work are very similar, right? Work, it delivers energy to a system. Work is F times R. R is usually like maybe we're pulling a box over a certain distance, right? And what we're saying is, like, how much force are we, how much force are we adding per second? Like, if we have high power, it means that we're delivering energy really fast to the system. So our change in this quantity over time, over a small period of time, is like really high. For example, like, we're increasing the kinetic energy of a ball, like, really fast. We have very high dE dt. So the way to think about this is, like, low power is kind of lazy. We're performing work at a slow pace. Our change in energy, our change in work over time is very slow, versus high power, our change in energy over time is really fast. Oh, if there's no change in energy over time, if your energy is constantly being delivered, then there's no power. So yeah, power is the rate. And another way to think about this is that since P is equal to dE dt, and we know, like, work is equal to F times, R. We could also write this as like F times X, where X is the displacement vector, just changing the variables. Maybe if I use this. Then if we just substitute this in, we get dF dx dt. Well, we can say, like, if the force is constant, for example, if the force is constant, we can take it out of the derivative. So then we just end up getting F times dx dt, which is just F times V. So if the force is constant, there's multiple ways where you can change the energy, right? You can change the force, or you could change the displacement. So in this case, we say, like, suppose you're pulling an object at the same rate. Then we say that the power is equal to that force times the velocity. And yeah, that's what power is. And power is measured in what? Gonna look that up. It was a joke. Ha ha ha. And yeah, that's it for today. As usual, we'll stick around for any questions. Thank you all for coming, and we'll see you next week. Take care.